Hello students, the question says a certain number of spherical drops of liquid of radius small r coalesce it to form a single drop of radius capital R and volume V. If T is the surface tension of the liquid, then so as given four options. If you notice it carefully, here the answer is given in terms of volume. So we have to find the surface energy of initial droplets and final drop in terms of volume. So let us see this situation. So we have these small drops of radius r and they became larger drop. Before getting into the quantitative part, like using formulas to solve the problem, let us try to predict the answer based on only the concept. When drops are added, suppose if you have a table and if you keep on adding the drops on the table, you will notice that naturally by themselves, these drops would become bigger drop. You no need to take a spoon and mix them. So if you just keep on adding the droplets, one drop after another drop, one drop after another drop, most of the time they will become a bigger drop. So if this process is occurring naturally, so in all the natural process, it would be an exothermic process. So we can say that in this situation where these small drops are mingling and they are becoming a larger drop, the energy is actually released. So we can remove these two situations where it is given energy is absorbed and energy is released. Why? Because in all the natural processes that are naturally occurring, so it would be an exothermic process. And another example could be if you made a water bubble and after some time that bubble would burst into smaller droplets. And these smaller droplets would even afterwards, they will merge into a bigger drop. So a bubble bursting and becoming smaller droplets is an exothermic reaction. That means energy is released. And even these smaller droplets becoming a drop. Don't be confused between a drop and a bubble. So this is also an exothermic process. So all natural reactions, generally which are occurring on their own, the energy would be released. Now let us come back to this problem. So we have n droplets and it became a larger drops. Let us find what is the energy, initial energy. So initial surface energy is equals to U initial is equals to, we have n droplets, so n into surface area into surface tension. This is the formula for surface energy of a drop due to surface tension. So U initial is n into surface area is 4. Since it's a sphere, we can assume droplets like a sphere. Even though I have represented them like a bubbles, they are technically droplets. So they will be in this way. So I hope you understood it. So 4 pi into small r square into surface tension T. So this would be initial energy. But as you can see in the options, everything is given in terms of volume. Since it is in terms of volume, I have to bring volume into the picture. We know n droplets, each droplet has a volume of 4 by 3 pi into r cube. It together represents the total volume V. N droplets, each droplet has a volume of 4 by 3 pi r cube. Now from this, if I carefully remove 4 pi r square on one side, we will have, and n into 4 pi r square on one side, we will have r, another r left from r cube divided by 3 equals to V. So from this we can write U initial equals to, in place of n into 4 pi r square, we can write 3 capital V by T. I will bring this 3 to this side and we have this V divided by T. So what is initial energy? Capital 3V by T into, we have this R also in the denominator, into 1 by small r. Let us do the same thing for a larger drop. So final surface energy U final equals to, again surface area is 4 pi r square into surface tension T. Again same thing, the volume of the larger sphere is 4 by 3 pi r cube. It is given as capital V. You might wonder why initial volume is equals to final volume. We will assume while solving these problems, we will assume that the density is not changing. If the density is not changing, again, I will repeat, this is also a droplet only. This one is also a very, very big drop. So if you assume constant density in this entire process, we can write initial mass equal to final mass. Since initial mass is equals to final mass, we can write mass as density into volume. So we can even conclude that initial volume would be equal to final volume. So I'll just do it by the, we can write initial mass is equals to final mass, and mass can be written as density into volume is equals to density into volume. If density is same, we can say V initial equal to V final. So that's why I'm equating 4 by 3 pi r cube also to V. From this, here we don't have any n here because it is a single drop. From this, 4 pi r square would become 3 into V by capital R. Let me just substitute that. So U final equals to 3V by capital R into T. So we got 3V T by R. There is a small correction here. It should be 3V into capital T. So we got 3VT into 1 by R. We got 3VT by R. So based on this, we can write change in potential energy or change in energy or energy released. If you say release, we have to do initial minus final. The reason we are calling it release is that most of these processes, since they are coalescing on their own, it's an exothermic, so they are losing the energy in that process. So let me write it 3VT by small r minus 3VT by capital R. So if you get 3VT common, you will get 1 by small r minus 1 by capital R, which is nothing but, I think it is my option C. I hope you understood how I have solved it. Most important thing in this is trying to understand the situation qualitatively rather than quantitatively. Here, n droplets by themselves, they will merge into a larger drop. Since they are doing themselves, so it's a natural process. In most of the natural process, it's an exothermic energy is released from that process. So without even using pen and paper, we can say it would be released, and we can eliminate these two options. And how much is released if you want to do, you have to do it quantitatively. I hope you understood the difference, and I hope you understood how to solve this. Thank you.